All right, let's get started. First, I want to thank Lenaro for inviting me to speak here. And more importantly, I want to thank everyone that's attending. I know your time is valuable, and it's great that you've decided to take some time to hear what I have to say. Hopefully you're here for hearing about some fleet monitoring solutions for IoT. So let's dig in. So real briefly about me, I'm an embedded Linux engineer, got about 25 years of experience, and the last 15 or so has been strictly in embedded Linux, primarily focused on the Yocto platform. I'm currently employed as a solutions architect for the Horizon platform, which is an embedded industrial embedded Linux platform for connected devices that's developed by Toradex. You see my contact information at the bottom. Feel free to reach out to me if you have any questions or need any follow-ups based on the information we're going to be discussing today. So what are we going to talk about? I'm going to start with the definition of fleet monitoring. It's a pretty broad topic, it means a lot of things to different people. So I just want to kind of level set so that we're all on the same page about what we're going to be discussing in the context of this talk. Then we'll talk about the architecture of a fleet monitoring system. We'll start talking about the general architecture and how it has evolved from its use in the enterprise IT space. And then we'll talk real briefly about some of the differences that are being in an Internet of Things device will necessitate to the architecture. Then we'll review a couple of the options that are out there, specifically focused on the options that we chose for the Horizon system and the reasons why. And then we'll finish up with a proof of concept implementation in Yocto that you should be able to take back to any Yocto configuration that you have and get up and running on your systems without any major issues. So, as is often the case when I start researching a topic like this, I start at the font of all human knowledge, Wikipedia, and you see the link there for fleet management in Wikipedia. Unfortunately, we got a bit of a language overloading problem. Most of the discussion in Wikipedia is around commercial motor vehicle fleets. There is, I guess, a bit of overlap, but in terms of what we're looking at, it's a bit different. Essentially, what I'm considering part of fleet monitoring is periodic monitoring of data from all the devices in your fleet. Your devices could be consumer devices, and you're getting information back from them. It could be telemetry, could be log information, and you want some mechanism to analyze that data and to visualize that data in what they call a single pane of glass. Essentially, that's a dashboard where you can kind of get an at-a-glance view of your entire system, your entire device fleet, and be able to spot problems and head them off before they become a major issue. And in terms of out of scope items, for at least for purposes of this discussion and the proof of concept that I've implemented here, we're not going to be doing any kind of remote access or remote control. Although those kind of features are very often combined with a system like what we're talking through here. And also, we won't be looking at use case dependent things such as machine learning, AI, predictive maintenance, things like that. Certainly, this could be expanded to get into those kind of use cases, but for now, we're looking at just basic infrastructure for getting the data back and visualizing the raw data. So, what do you want to view in your fleet monitoring system? There's it's going to depend, of course, very heavily on your use case. But there are some things that are very common. Device health, obviously, that's a fairly common thing. When you have a large number of devices out in the field, you want to know how many of them are online, how long they've been up, what's the status of all the software running on it, are you having any temperature issues, that kind of thing. Resource utilization, that's the first one that most people will see. That's things like CPU usage, memory usage, how much space you got left in the block devices, how much network bandwidth are you sucking up with your device. And they can also go one level down and get you information about all the stuff that's installed there in terms of kernel versions, bootloader versions, packages, containers. There's all kinds of information you can pull back. Other things that are very potentially very important is anytime the device status changes. So you have a device out there, it was going along, all of a sudden you get a failed health check. That's definitely something you want to be able to flag and take a look at before it becomes a major issue. Similarly with updates or just in general, any software that's running on the system, when it starts showing issues, you want to be able to detect that. And closely related and generally considered part of a fleet monitoring system is the ability to look at logs, whether that's from the kernel, from your applications or your containers, or from the systemd system init system if you happen to be running that in your system. And just to mention a couple non-functional requirements that you want to keep in mind when you are reviewing these systems, are the systems open source or not? Is that important to you? Are they on-prem or hosted? Obviously I can't tell you what's right for any given application. It's going to depend heavily on your use case and your application and your budgeting and that kind of thing. And what are the performance and resource requirements? Server-side performance is a concern, but especially in the world of embedded devices or connected, IoT devices, you're typically looking at resource-constrained devices. So you want to make sure that the client-side performance is adequate, and that the fleet monitoring system that's running on the device is not taking up too much of the resources of the system. And finally, you want to make sure that it's, you have the ability to integrate it with other services. Typically, most of these connected device fleets are monitored by more than one system. You might have a fleet monitoring system, and you might have a separate IoT system, a separate OTA system, and you might have, other systems you integrate with, whether that's, Google Cloud, Azure Wave, things like that. So you want to make sure that your fleet monitoring is going to be flexible enough to let you properly integrate with all the systems that you'll need for the life cycle of your product. So general architecture, you see the diagram here. It's pretty straightforward. You're able to take inputs from many different sources, whether that's things like SNMP, some local file information, cloud APIs. As I mentioned, most of these systems have come from the enterprise IT space, so SNMP is big, cloud APIs are big. You see in our diagram here, we're pulling some input from onboard sources, so that could be things like CPU usage, memory usage, that kind of thing. We're also pulling some devices from offboard sources. That's where you would get into things like SNMP, cloud APIs, and that kind of and such. Additionally, you've got some local filters that allow for some processing on the device. You can filter out certain things that you're not interested in. You might even be able to do a little bit of manipulation of the data before you send it up. And then note finally that there are the ability to send it to multiple output streams. So this is very useful when you're sending it. You're sending it to one system or another. You might send it to an Elasticsearch database, which is what we're going to do in the proof of concept today. And you might also send it to a different. You might have your own cloud service that you want to send data to for additional processing for some of the things that are not supported by Elasticsearch, such as the machine learning and AI scenarios that we're ignoring. Now, how does this change for IoT? Typically, IoT devices are resource constrained. They're much more homogeneous. So, in an enterprise IT space, you're going to have a lot of different kinds of devices. You're going to have some servers, some rack mounted servers, some desktop servers. You're going to have laptops and that kind of thing. So you're going to have a lot more different kinds of devices. Typically, when you're looking at an IoT fleet, they're all within one or within just a handful of different device types. In a lot of cases, they will be installed in networks that you don't have control of. So typically, you're not going to see the offboard data collection sources like we saw in the general case. But the rest of the system is going to be pretty similar. You're going to have filtering devices, the filtering capabilities on the device. You're going to have the ability to output to multiple devices. So that's the primary difference here is that you're not going to be you can have a much more homogeneous infrastructure pulling information mainly from the device itself. Now let's look at a couple of the options that we reviewed and discarded. And the primary reason for all of these really is that they're enterprise IT focused, they're fairly large, a lot more complicated than we needed for being able to integrate into our Horizon system. Nagios Chi, you see here, they've got a nice online demo server. You can log in and play around, and you'll see that it is a very large system with a lot of configurability and a lot of options. It does use SNMP or custom agents running on their devices. It does have a hybrid open source licensing as well as commercial licensing, and Yocto recipes do exist. So it is possible to get this up and running in a Yocto environment. Elasticstack, I mentioned Elasticsearch, also called ELK, Elasticsearch, Logstash, and Kibana. These three components make up a fairly complete system that can gather this data, allow you to store it, filter it, and visualize it. Lots of input plugins are available. It is available either on-prem or hosted, and it is under a dual license with Apache 2. At the moment, it does have a relatively large on-device footprint, which is the reason we decided to pass on it. But they do have something called Beats, which is intended to minimize the on-device footprint. Datadog, they're obviously quite popular now. They're the only ones of this list that explicitly mentioned IoT monitoring. I've got the link there if you want to take a look and see what their IoT solution is. But they, as near as I can tell, they're completely closed source with a proprietary license. Zabbix, you see the quote there from their website describing their system. Again, there are Yocto recipes. It is fully open source GPL v2, but it is a fairly large enterprise focused system. And the last one that we looked at was called Splunk. A lot of people have heard of that. That first line there in the text, that's actually their description of the system. It is on-prem or hosted. They are a commercial license, but do have a feature limited free trial, or free option. And as far as the options that we considered, the first one we looked at was called Telegraph or an InfluxDB. It is available both on-prem and hosted. It is open source licensed. It is written in Golang, which is nice because that means it will compile down to a single binary with no external dependencies. However, it does require a fairly large on-device footprint, 110 megs of flash, which is for some of our devices quite significant. So we kept looking and we came up with FluentBit, which is open source under the Apache license. It is part of the Cloud Native Computing Foundation. There are two clients, FluentD, which is written in C and Rust. That's the big one. You can see how many plugins it has available. It does depend on Ruby gems, so it does have some external dependencies, which does increase the amount of flash storage that it's needed in your block file system. Whereas FluentBit was specifically designed for resource-constrained systems. It's written in C, a much more limited set of input and output plugins, but there are no external dependencies, and you can see how much smaller it is in terms of both RAM and flash. And there are Yocto recipes that exist. In fact, they're maintained as part of the FluentBit project, which is pretty nice. So as you might have guessed, we ended up choosing FluentBit, the client agent. As far as the server side, at the moment, we have a custom output plugin that will deliver JSON to our cloud server through an in-band data channel that's part of our normal transport between our devices and our cloud. But since it's full FluentBit, you can still use on-device filters to send data to a separate destination, such as Kibana, like we're going to look at here in a minute. And at the moment, we're pulling in a lot more data than we're actually visualizing in our server side, but over time we'll have that more full featured, and we'll probably also wrap that in an API. So if you want to use our system, you're able to actually get access to all this data without necessarily having to deal with the complexity of scaling and everything that you would need to do to be able to run a cloud system like this. So the proof of concept, obviously, it's FluentBit and Yocto, as we've been discussing. I've implemented a custom distro and a custom image in a public Git repository. It's pretty straightforward. It's basically just Yocto's core image with a couple extra packages and some configuration for FluentBit. And it is set up to deliver to an Elasticsearch instance, which can then further be visualized in Kibana. So let's take a look at how that works. And I want to stress that this is not a Horizon setup. This is actually just a straight ahead Yocto configuration that you run on your local system, and the server runs locally as well. So how do we set this up? The device setup is pretty straightforward. You're going to check out my Metafleet monitoring POC layer. You're going to add that to your bblayers.conf. You're going to set the fleet server URI to whatever the IP address of your server is. And then you're going to run bitbake for the fleet monitoring POC image. Fairly straightforward stuff. Server side, you'll inside the MISC directory in that repository that you just checked out, I've created a Docker Compose file that will start both Kibana and Elasticsearch. There is no security built in here. This is the Elasticsearch engine in this case will accept data from any device that connects to the appropriate port. So I want to stress again that this is a proof of concept and not intended as production code. So let's take a look. So this is my server. You can see here I'm running both Elasticsearch and Kibana. You see what ports they're listening on. Kibana is listening on 5601, which is the graphical web interface. I've got two devices running here. I've got a Kimu device, and you see that it is running FluentBit. And I've got an Apellis IMX device, which is a IMX6 physical piece of hardware here on my lab bench. And we can see that it is running as well the same FluentBit daemon. So now let's try a few things before we get into the full server side and visualization. Let's just take a look at what FluentBit provides. So this first command I'm going to run, this is FluentBit reading the CPU usage information, and it's writing it to just using the standard output plugin. It's selecting all the entries that it reads, and it's going to output them every 1 second. So every second we see another piece of JSON data pushed out with all the CPU usage information that's available in the system. Not terribly exciting because you're not usually going to use standard output here. There's much more interesting ways to gather and collect this data, but it is a useful tool to help us know that the system is up and functioning. And we'll take a look at another one. So in this case, it's the same basic thing, but now we're looking at the memory information, free and used and swap. I don't have any swap enabled, so that's not terribly interesting, but at least you do see some of the amount of free memory changing up a little bit here. So you see that it is actually pulling new data each time through the loop. And one more thing I want to do, just to kind of give an idea. If we take a look at this fluentbit.small configuration file, this is a very simple configuration that I've set up that allows you to, it will take the CPU usage information that we just looked at. It's going to nest it in a JSON object just for simplicity's sake. And then it's going to deliver it with the TCP output plugin to my server that we're looking at, just raw JSON lines on port 8850. So this is not, I'm going to create, using the netcat utility, I will create a server I will create a server instance listening on port 8850. And we're going to dump that output through the JQ beautifier so that it prints that information in a nice, easy to see format that we're able to read. So let's see, we have to tell FluentBit to run with a specific configuration file. So now we see that it's running. We won't see anything here, but if we come back over to our server, we'll see every second, we'll see that same basic information is now coming across to another server. In this case, it's going to be visualized just in text using the JQ system. So we'll go ahead and kill that off. And we'll kill this server off because we don't need those anymore. Now we know that this system is running FluentBit in daemon mode. And so we can come over here to our proof of concept. This is the Kibana visualization of the data in Elasticsearch. At this point, I have two different pieces of data being visualized here. And actually, let's jump back over here. We'll take a look at the some of the input files. If we take a look at the input file for the thermal, you'll see that we're gathering thermal information as input. We're outputting it to Elasticsearch, just telling it where the Elasticsearch instance is located. And then we're using a filter to actually add records to the data. So in this case, I'm adding a record with the host name, which allows us to adjust the visualization. So since I have multiple machines, I'm able to actually see data from each individual machine. So back over here in our proof of concept, you see this is the CPU usage information that we looked at a minute ago, and it's separated out by color based on which machine it is. Similarly for the amount of memory used. So, you know, both my systems are sitting there delivering data to the Kibana instance, and it's being visualized in real time. Now let's go ahead and create another one. We'll create a visualization. And so what we want to do is search for temperature. And we're going to go ahead and select temp. We're going to visualize the temp. And then the other thing we want to do is look at the host name. And we're going to break this down by host name, which is how we get the multiple colors. And then we'll go ahead and save this. And now we have a third visualization in here. Interestingly, the QEMU arm doesn't have any temperature measurement, not surprising since it's running emulated, but we now have a new visualization to our system. And just to make sure that all this is actually doing something, let's jump back over here and I'm going to run a stress test. So this is a stress test utility that does some matrix multiplications and things like that to help stress your system. And if we jump back over to our visualization page, you can see obviously the CPU utilization has gone way up. Memory utilization is going up as well. And as expected, the temperature of the system is also rising. And if we come back and kill off our stress test, and then come back into our visualization, we'll start to see these numbers settle back down to what they were at steady state before we started that test. So with that, I'm going to be around in the chat for a little while, trying to make sure I answer everybody's questions. You see my contact information on the screen here. If you have any questions or just want to chat about anything we discussed here, feel free to reach out to me. I'm always happy for the feedback. Thank you very much, and everyone have a nice day.